So my presentation today is taking what Alex shared yesterday morning about the fundamentals, or yesterday afternoon. Alex's presentations yesterday about the fundamentals of risk and risk reduction, and looking at those fundamentals through the lens of some communities projects. And of course, that raises the question, what is a communities project? So at BGC, we have divided the work that we do into a few different sectors. We have a sector that is mining projects. We have a sector for transportation that includes roads and railways. We have an energy sector for hydro projects. And then the sector that myself and Alex and Lauren actually work on most frequently is our community sector. And this is risk management for homes, for critical infrastructure, for businesses, and to some extent as well, like lifelines, so access to those communities and utilities for those communities. So whatever communities need to be functioning well. And similar to Lauren's point yesterday about roads and linear infrastructure, communities in mountainous areas are subject to mountain hazards, and there is a whole range of different hazard types that can affect communities depending on where the communities are located, and with respect to proximity to mountains, or as we get down into the lowlands. And so that can be direct impact from glacial lake outburst floods or from landslides, or as we move into the mid-hill, this is more flooding and other types of concerns, and sediment deposition, river aggradation. And then, of course, the other piece that we see happening around the world and in the Himalayas in particular is that these hazards are increasing due to climate change and glacial melt. And so this is the Chamali example that I'm sure you're all familiar with, but there are many other cases like that. So not only are communities contending with this baseline problem of risk, that risk is also increasing as the hazards change with climate change. And so our goal when we are working on geohazard risk management for communities is to use the available resources to effectively manage risk. And this gets to, so available resources. I want to take a couple minutes here to, maybe this can be an open discussion. What resources are available to communities to manage geohazard and disaster risks? So if you think about maybe the town that you grew up in, or a town that you've been working in, or even the city of Kathmandu, what resources are available to manage disaster risk? Feel free to put a hand up and so things, I can start the list maybe. Resources that might be available are things like, what budget does that community have? How much of their money is available for maintenance or for building new structures? What other resources might a community have?
Basically in Nepal we have district disaster response committee. So always be able to respond this kind of disaster.
Yeah.
During the time of disaster, and it is all over the Nepal.
Okay. Yeah. So there's funds available from that. What about in terms of people or capacity? Can anyone? If you're going to design disaster or geohazard risk management, you need someone who knows how to do that. You need a professional. You need an available engineer. You need maybe a planner. You need somebody who can support the design process. Any other ideas of available resources? Yeah?
Also,
thanks, Alex.
Red Cross Society in every district, and they have quick response materials like safety jackets and other tents and other equipments like to respond to disaster. So
that's a good point.
And also we have engineers in every municipality nowadays and technical personalities who can respond the disaster at the time of the disaster.
Excellent. Okay, so there's emergency response. There is some equipment ready, and there are some people trained to respond once a disaster occurs. Any other ideas of available resources?
I think in some disasters like large playground at the community can also be a type of resource while of the settlement also.
Sorry, I cut out for
Yes, during emergency evacuation operation during the earthquake, the playgrounds inside the communities can also be resources.
Okay, yeah, so a safe place for people to go
Yes.
where there's not buildings that will fall down. I'm hearing a lot of good answers about what can be done once a disaster occurs. What other available resources or want to have available before the disaster? Yeah.
The early warning system, way of communication during disaster, some endogenous knowledge within the community how to cope in the situation of disasters, and then the enabling environment like the framework policies, kind of things. Suppose that community or the has their own disaster plan or not, and then people are aware of this kind of things like this is the place for evacuation, or if they have in hand document, simply if they have their emergency kit or not in their home in a bag, and they have the knowledge of disaster and impact. So it depends upon the situation as well.
Yeah, no, there was a lot of good things in that answer, but I think I heard that the community needs to be aware of what areas will be impacted by the hazard. In some cases, there may be early warning systems, and then there needs to be community education is another resource, so that people know how to respond when these things occur. Yes?
In my local government, we use land use planning, especially local area plans, to designate the high-risk areas. We call it precinct, we designate it as E1, that means nothing is allowed to build there. So that's how we protect and keep the settlement away from disaster risk area.
Excellent. Thank you. This has been a great level to, oh, sorry, yes.
At central level, there is the National Disaster Risk Reduction and Management Authority, which is under Ministry of Home Affairs. And at provincial level, the activating body is Ministry of Internal Affairs and Law. And at municipal level, there are rescue teams or municipal committee. Also, there is basic use of hazard mapping in all over the areas in Nepal. Besides this, other NGOs and INGOs are activating bodies to fight with the disasters. We have various community networks in local levels also. Yes.
Thank you. Yeah, this is great. There's
Talked a lot about organizations, and
Yes.
what I'm trying to say is something very basic. So when you go to the community, what I think is we do have community leaders from different castes or different communities that can organize or that can convince people to come, and they will listen to that particular person. So training that person, making that person aware of it, and asking him to relay those messages to the community people could be one of the resources. Along with it, we also have traditional things that people have been using from a really long time, like we talked about cascading. So traditionally in Nepal, you can see people farming in cascades, like they are creating they're boring holes. I wouldn't say hole, but like a basin, smaller areas where they can store water. So those they don't know the engineering impact, but they have been utilizing that from traditionally, right?
Yeah.
So we can identify those and to make them aware about how it can impact or how good of an engineering it is. They don't highlight
reinforce good
yeah.
behaviors that they
Yes.
already have.
Yeah, so we can actually promote those traditional things that they have been using, along with implementing the knowledge, engineering knowledge, the benefits awaiting them. So that could be some of the resources.
Excellent. Yeah, I'm hearing a lot of awareness. Yeah, so we've talked about, so the goal is to use available resources to effectively manage risk. The next piece of this statement that's potentially more challenging is, so we have some sense of what available resources there might be. Now I'm curious to hear from everybody, about what does effective risk management for community look like. So we've talked about what resources might exist in theory. Maybe they're there in terms of the policy is in place. But from your perspective, is that effective? Is that are those resources being used, or are there gaps in terms of effective risk management? Or what does effective risk management look like for a community? What would a successful story be? Let's see if we have any ideas to start. No?
In our country, there is the provision of preparing disaster preparedness plan for every individual local government, and which is basically for the fire hazard, landslide, and other water-induced hazards. And it might be the great planning for responding these sort of problems. And also, we have the provision to make urban planning things like what do we call IUDP, it's Integrated Urban Development Plan, which will also includes a disaster response plan within it, and that might be the very fruitful with the community during the time of disaster.
Thank you. Yeah. To touch on how to effectively manage risk, I heard a lot of people mention the points about there needs to be the community capacity, there needs to be awareness and education. So it's not just having these things existing as institutions, they also need to be tied in with that specific community so that there's strong connection and there is ability to access funding, ability to access the information like the hazard maps, and there's knowledge about how to use the hazard maps or the early warning systems or the tools to actually make good decisions. And so we talked about that one already. So what I'm hoping to talk through today is a little bit about how we approach this goal through the lens of a couple cases in Canada, and then we can have some more dialogue about what it looks like in Nepal as well. And through the cases I'll be talking about, we'll also be returning to this risk management framework that was introduced yesterday, and looking at how we've used this framework to support communities to use available resources to effectively manage risk. And we will also be looking at the site-specific risk management framework. So the two cases, and I'm not sure that we'll actually, this is where I was saying we're going to potentially split up some of the content today. The two cases that I will eventually be sharing about are both located in Western Canada, and these are projects that I've been involved in for more than 10 years, on and off in various ways. The first project we'll be talking about is in Canmore, near the city of Calgary, in the Bow Valley, and this is in the Rocky Mountains in Canada. And then the second project we'll be talking about potentially tomorrow is in the town of Squamish, which is actually the town that Lauren and I live in, where we've been working on managing a very large rock avalanche risk that could impact the community there. So starting with Canmore and the Bow Valley, I'll give you a bit more of a project introduction. Why are we working in this community? What are the hazards and what are the concerns? And we'll talk about the application of the risk management framework in Canmore. And in this particular case, that included short-term mitigation, regional prioritization, as well as some long-term mitigation. And then I want to share some of the lessons learned that I've come up with through my involvement in this project in the last 10 years. Some of the things that I made mistakes with, that I would do differently if I could do them again, that I hope are useful things for you to understand. So BGC's involvement in the Canmore area came following what was for us in Canada, or in this area of Canada, a very large rainstorm. So in June 2013, there was heavy rainfall that caused flooding on many of the rivers in Alberta, Canada. This is the city of Calgary. This is normally kind of like a sports field area. It might be hard to see from the back, but all of the roads, the parklands, everything is covered in water. So this area is all flooded here. The rainfall that fell, this is an annual maximum 3-day rainfall, was about 250 millimeters, which here in Nepal is not very much, but for this area of the world is quite a lot. So that meant that none of the infrastructure was designed for this amount of water. And so there was flooding on the major rivers, but where BGC got pulled in was as we moved into the mountains and the mountain hazards, there were debris flows and debris floods that caused highway closures and damages to communities and to development on these steep creek fans. And you'll hear us use the term steep creeks. Lauren probably used it as well pretty commonly. That's a term that we use just generally to describe steep creeks that are prone to debris flows and debris floods. And so here's kind of some snapshot of some of the damages that occurred. So there were creeks that had debris flows or debris floods that had avulsions, so that the creek left the typical channel and went a different direction in impacted houses. There were sites where Cougar Creek, if you visit Cougar Creek in the summertime, you can jump over it. It's a little creek, and it went to 40 meters wide, and there wasn't space, so there was a lot of bank erosion, and there were houses impacted, and we'll talk a lot more about this site because it was very important. But other cases where the roads were impacted, there was flooding, lots of issues here. Here are a few more. Oh, this is specifically on Cougar Creek was where the major damages were. So I was mentioning that there was bank erosion that impacted houses. And then that same highway that Lauren was talking to us about yesterday, the Trans-Canada Highway, Highway 1, our one big highway across our country, also crosses the Cougar Creek fan. And this is what happened to the Cougar Creek fan, or to Cougar Creek and the Trans-Canada Highway. And you can see the truck traffic here that was backed up. Do you remember how long it was closed for? I believe it was closed for a couple weeks. A week, yeah. And so all of the transport traffic, the shipping traffic, the businesses in the area, this affected so much beyond just the Canmore region or the Calgary region that was directly impacted by the floods. This affected businesses across Canada because of this closure. And so this was a major concern for the community. So there was not only many additional sites, there was also this one kind of priority site. So BGC was engaged after the event to support the local communities to manage geohazard risk. And so this is when I'm saying the Bow Valley is the Bow River was the river that runs through the mountains here. And there's a few communities along this area. So there's the major road and then the villages and the towns here. And this is an aerial image of the area. So you can see that there's a fair amount of development. And as well, this landform here, sorry, my mic is kind of falling off. Let's get that sorted. There we go. This landform here is the Cougar Creek fan. Does everyone know what I mean when I say fan? Yes? No? Do you want some definitions? Okay, yeah, so over time, so debris flows, Alex showed yesterday the spectrum of landslide process types. At one end, there was floods, lots and lots of water, not so much sediment. At the other end, there was something like a rock fall or a rock avalanche. All rocks, no water. Debris flows and debris floods are somewhere in the middle of that. They're the mix of water and sediment. And what's somewhat not unique, but specific to debris flows and debris floods is they occur over and over again in the same channels. And so over time, as those events occur, they're building up a landform called a fan, because it looks like a fan. And what that has a few implications for us as professionals trying to manage these hazards. It means that We know that they're always going to occur over and over in these same places. We also, and I'll touch on this a little bit later, but we can use the fact that this fan exists to understand, and the fact that the fan has been built up by many events occurring over and over again. We can study that fan and understand what might happen next or what could happen in the future. And then the other piece to recognize as professionals about debris flows and debris floods is that even if you show up on a given day and the channel is here on the fan is like this, and the channel is here, over time, the channel wants to be moving around. If left undeveloped and to its kind of natural state, it would want to be moving around. But often, we show up as humans and we want a place to develop, to build houses, to build schools, to build our communities, and we turn the fan into something like this. I don't know if you can see very well from the back. Oh, I can zoom in theory.
Just touch it with one finger.
Oh, I did it. Okay. So this is the Cougar Creek fan. The channel comes right through here, and there was development put on this fan right up to the boundaries of the channel. And this is something that you see over and over again on alluvial fans around the world. This is very typical. But for us needing to manage the geohazard risk, it's something that we need to look at and pay attention to and make a plan for, because the creek does not want to stay there. It wants to move around. It wants to go big. It wants to erode the banks. So this is where we were brought in. Oh, I did it. Okay. All right, so after the event, I'm just going to go back to this one for a second. So we've talked a bit about Cougar Creek. Cougar Creek is this big black shape here. All of these other black polygons are other sites that also had debris flows or debris floods in this event. So we know that Cougar Creek is a problem, but we also have many other sites to deal with. So we can't do everything at once. What should we do first? We have 20 different fans within the study area. We have one identified high priority site. We know that Cougar Creek is the priority to start because there was so much damage, because of the big highway closure, and because there's so much exposure on the Cougar Creek fan. There's lots of houses, there's the school, the hospital, the highway. And then of those 20 fans within the study area, we had 10 that either had more development on them or that just had larger events in 2013. So there was more concern about them. So how we approached this is we looked at, because we already knew that Cougar Creek was a priority, so we can follow this path, we were jumping for Cougar Creek right to this site-specific risk management design phase. And then for those other sites, we were working through the prioritization exercise. And this was all happening in parallel because there was a lot of, as I'm sure you've seen, when there are disaster events, there's a lot of urgency to make steps to show that we're solving the problem and to reduce the risk and improve things. So in this presentation, we will walk through both what was done for Cougar Creek in terms of short term, and then also looking at some of the regional prioritization. All right, maybe I should stop. Any questions about Canmore and the project introduction I shared? Is there any other information that would be helpful to understand? Cougar Creek short-term mitigation. As I said a minute ago, we're jumping right to that site-specific design phase because we know Cougar Creek is a priority. We know we need to reduce risks. So we're going to walk through this framework of identifying the risks, identifying the risk reduction options, using decision tools, and then doing detailed design of a preferred alternative. And what have I put in here? Okay. So I think this is a good moment. So I mentioned when I first came up on stage that there was maybe some confusion about exposure, the difference between exposure and vulnerability. And I think since we're reaching this point in this case study, this is a good time to talk about that. And I think that's something, how do you make it be a whiteboard? How'd you do that? Oh, is it this thing? But that's just to draw in here, right?
Yes.
I don't want to draw on this, I just want the plain one. Okay. Okay, wait, actually there is how we would walk through identifying risks for Cougar Creek for short-term mitigation and walking through that process of hazard identification, exposure identification, and vulnerability identification. And as we were discussing last night about how to kind of share these concepts a little better, one thing we recognized was that when we have been talking about hazard, filling out that Venn diagram with the circles, oh, this isn't going to let me write, we'll see. We've almost always been talking about process type. In the examples we've been providing you, and when you're doing it at your tables and I'm seeing people write down what's the hazard, what we've all been missing, us too, this was us teaching it, is these two pieces. The size and intensity and the likelihood. So not only is a hazard the process type, the debris flow, the debris flood, the rock fall, but you also need to have some sense of size and intensity. And so I think you're right. I think I have to stop sharing to get the whiteboard thing.
Bottom right.
Oh, and then it.
Oh, sorry, actionable.
Yeah, how did you get to that? This thing. Okay, great. Okay, so. Okay, so we've been thinking about hazard, exposure, and vulnerability. So we have. Kind of feel like. So this is a watershed, and this is the source of, excuse my very poor drawing skills. When I went to I'm just going to tell a little story for a minute. When I used to go to the field as a junior engineer with my mentor, and at that time, he was still a little bit old school, and so he didn't always like just taking pictures of the sites we went to. He wanted us to draw, like make a sketch of the things we were seeing in the field. And at first, when we went out, he would say, okay, Emily, make a sketch of the thing we are seeing, of the channel and the trees and the landslide. And then he would look at a couple of my sketches, and then he stopped letting me do the sketches. He would do the sketches, and I would take the other notes. So bear with me, but this is a watershed. Maybe we have some landslides coming in, and then we have our fan. And we have a community on this fan. We have some houses. All right. And so let's say this is a debris flow site. So the hazard is a debris flow, but it is also the debris flow of a certain size and likelihood. So let's say the 10-year debris flow looks like this. Then when we're thinking about exposure, so let's do something over here. 10-year. So the hazard is the debris flow. The exposure is then what is exposed to that hazard, which is the 10-year event. So it's this house. So we can say, I don't know, one house. So exposure is one house. And then the vulnerability is how vulnerable, how much damage there would be at that house in that 10-year event. And so you're gonna have your hazard probability, you're gonna do some runout model to figure out how far it's gonna go. The runout model will tell you maybe how deep it is and how fast the flow is moving at that house. So you know the house is affected, the one house is affected from your model, and then your vulnerability is in that 10-year event that's 2 meters deep and moving at 5 meters a second, how much damage will there be at your house? And maybe let's say there is a 50% chance of fatality, and there is loss of 30% damage, say. So 30% of the building value is lost. And then, if we were to do that same question, this is not the only size of hazard that could happen from this channel. Debris flows come in all different sizes. You can have the small one that happens more frequently. You can have the big one that happens less frequently. So if we were to work through the same process for a 100-year debris flow, let's say that I run my, I do my analysis, I figure out how big that 100-year event is, I do a runout model, and the 100-year event goes this far. So it's a debris flow, but then it has a certain size and frequency. What would be the exposure for this event?
3 houses.
Yeah. And then the vulnerability, right now I'm kind of making up numbers for an example. How you would actually determine vulnerability is something called like a fragility curve. And that relates the hazard, so the damage from the hazard, the flow depth, the hazard intensity, sorry, that's the word I'm going for, the flow depth and the flow velocity to how much damage you would expect. And so you would have some relationship that's separately developed from other events that would give you an idea of if a 2-meter debris flow hits your house, you're this likely to die or you're going to have this amount of damage. And the same kind of relationship could be developed for a road or something like that. So that relationship is going to also be specific here. So say maybe this is, and actually the vulnerability would be different based on where you are. So this green line is the overall extent of the 100-year event, but the vulnerability is different at this house than at this house. Ooh. I'm good at this thing. Than at this house, because the hazard intensity is different. Okay. Any questions about this? Okay. I think what we tried to do yesterday with the Venn diagrams is to show the big picture of this. But this is, and we'll go in more detail, we'll keep bringing this up, kind of how to get into more detail in all of it. All right. Let's go back to the presentation. So this is the creek in Canmore that's subject to very big debris flood hazards with lots of development. It's debris flood. And specifically for this site, part of what was contributing to that hazard was that the peak discharge of the event was much larger than the channel capacity, and that was causing bank erosion. And so the bank erosion was kind of a secondary hazard. And you're going to see that I think this is maybe a problem throughout all of our slides. Often when we're putting hazard here, we're just saying process type, but behind every process type is those questions about size and frequency as well. So we'll talk more about that. What's exposed on Cougar Creek in general in the biggest picture was, let's see, so we have people that are living on the fan, buildings, and infrastructure. And then the vulnerability comes if a debris flood of a certain size impacts the building, and then that impact causes damage or potential life loss. Oh, don't need that one anymore. All right, so risk reduction options. And this was, I think, the thing to keep in mind about this example. This was short-term mitigation for Cougar Creek. And so the event occurred in June 2013. And the request that BGC had from the community was to have something in place to reduce the risk by the next spring. So by the time we were working on this, and actually Alex, I don't know where he went, but he led this project. But by the time Alex was really working on this project, he had about 6 months to come up with a design concept, finish the design, and then get it constructed through the winter in one of the coldest places in Canada, in order to reduce the risk for the community before the next freshet, before the next melt. So those were the constraints we were working with. So to start, what Alex would have done was come up with all of the things that we possibly could have implemented here. And then we'll go through that exercise of ruling off the ones that are crazy to do in 6 months. So maybe something you can do is stabilize the source zone, stop the debris floods from starting. You can retain or attenuate the peak discharge, so the high peak of the flood, armor the channel banks to stop the bank erosion. Exposure, in theory, if you had all the time in the world, you could relocate the buildings and infrastructure. You could use a warning and evacuation system, or maybe land use planning. And then vulnerability reduction would be things like, what can you do at the building level to reduce the susceptibility of that element at risk to the hazard? And so that's things like local protection, building the building stronger, putting a wall around the building, increasing the height, and then also public education. And then the next step here is to use decision tools to select a preferred alternative. And as I said, the key constraint was that short-term mitigation needed to be in place in 6 months. So pretty quickly, we can start ruling things out. We can't stabilize the source zone here. This watershed, although still much smaller than many of the sites you're dealing with in the Himalayas, is still a large watershed that is in the Rocky Mountains. They're limestone, and there's no trees. It's all just scree and rocks, and there's so much material, so you just couldn't conceivably get up there. There's no access as well. Other things we can rule out. We can't relocate the existing buildings and infrastructure in 6 months. There's a lot of things on this fan. We don't have time to do that. Similarly, land use planning isn't going to help. Land use planning is something that will work if the area is not yet developed. So we need something that will help us within this time period. Local protection, similarly, not enough time to do something like that. So what was left after this initial review? One thing that was left was a warning and evacuation system. So if we could have put a warning system in place that would perhaps trigger on a certain rainfall threshold and would get the people out. But on Cougar Creek, as Lauren talked about in her presentation yesterday, there's different types of risk that contribute to the overall risk. So there was life safety risk, but there was also a lot of potential for economic damages, and there was the major highway that we didn't want to have closed. So getting the people out of the way helps a little bit, but it wouldn't help enough. And so it was determined that was not a good choice here. Another piece that could be done would be emergency preparedness planning. This is something that came up as an available resource that communities might want to use when we were discussing earlier. It's important, it's very needed. It was something that the Canmore was trying to do a good job on, that the town was doing a good job on, but it also doesn't reduce the economic losses. And so the piece that was left was to retain or attenuate the peak discharge. So try to catch hazard reduction and try to reduce the debris and the sediment load that was reaching the community. And then to also armor the downstream channel to limit bank erosion. And so those were the preferred options that were selected. And so in this case, a flexible debris net was constructed in the channel upstream. This is the Cougar Creek channel just upstream of the fan. And this net was a custom net that was about 40 meters wide, 6 meters high. And it was selected because it could be built quickly. It was possible to build this within that 6-month period. It was possible to build this in the winter. It was relatively low cost. It wasn't going to be possible to do earthworks or concrete in this time. And the cost of this net was less than the value of one of the homes on the Cougar Creek fan. So in terms of the cost effectiveness for this particular site, this was pretty cost effective as a short-term measure. And then the other piece that was done was to put these articulated concrete mats all along the channel to reduce the potential for bank erosion. And these were actually something I'd never seen before this site. They kind of look like, do you have egg cartons here, presumably? Like, they're blocks of concrete, and they're wired together, and they come in these big mats, and you can put them in on the edge of the channel and lay them in, and they were relatively quick to install, and they were used because also there was no big rock left in the valley after the event. There was no riprap, so this was something that could be built and put in place pretty quickly. All right. So this was our answer for the Canmore short-term mitigation. Any questions on how this design process was followed? All right. About relates to early warning systems. So as I was walking through this Cougar Creek short-term mitigation example, I mentioned that early warning systems only reduce life loss risk. They don't reduce economic damages. And I think it's worth digging into that point a little bit more because often in North America, around the world, I have seen people in maybe government positions or policy positions suggesting early warning systems as the solution to all the problems. Okay, we have a debris flow risk, we have a geohazard risk, we'll put in an early warning system and we're good. Everything's okay. But there are limitations to how useful an early warning system can be, and I think it's helpful for the people in this room to understand that and then be able to communicate that to the people that you're working with when they say, okay, design an early warning system, it will fix our problem. Maybe it will fix some problems, but there's limitations to understand. So we're going to talk quickly about how early warning systems reduce risk and then what's needed for that to actually be effective. With any risk management that you're designing, anything you're doing as a professional practitioner, anytime, it's really, you need to know the purpose of what you're doing. So you need to match the risk management method to the need. And so, where was I going with this? Oh, right, okay. So you need to match the risk management to the need. So if you have a site where you need to look at what is exposed in your given site, and then of the things that are exposed, can an early warning system be an effective tool to reduce the risk for those things? So early warning systems are only useful really to reduce life loss risk. And maybe in limited use in community contexts for economic risks or damages. And then what needs to be in place for an early warning system to be effective? There's 3 things that need to be in place. There needs to be a way to trigger the early warning system. There needs to be a way to communicate once the early warning system is triggered. And then there needs to be a clear action that can be taken that actually reduces the risk. So let's chat a bit about the different trigger types. One, sometimes that can work. Then the other piece that often gets tried or we work on is to trigger upon rainfall or some other condition that might signal hazard initiation. And of course, then it's a secondary effect where maybe the rainfall will cause the debris flow, maybe it won't. And you've probably, and in this case, we've got a zone here with lower precipitation that's been designated as there's no, this is a low risk zone, a medium risk zone, and a high risk zone. And the blue and the red are non-events and events that have happened. And this is a pretend data set, but we have many, many real data sets that show that you get events that occur in low risk precipitation periods and non-events that occur in high risk precipitation periods. So there's a lot of uncertainty, and this type of trigger is not reliable. So hazard initiation triggers, limited time, rainfall, or other movement thresholds are unreliable. And then there's also the pieces of needing to communicate that in some way that the community can act on. And then they need to have a clear action that they can take. They need to have somewhere safe that they can go. So whether that's the playground that was mentioned in the case of an earthquake, somewhere, or it's a piece of elevated land that's been identified for evacuation, having those options available. So I think it's helpful to understand early warning systems are only useful under the right conditions. Any questions on what I've talked about so far, or additions from BGC team, if there's anything you want to say?
Among the people due to these early warning
Yes.
system.
Yeah, so that's a concern around,
Because false warning might also create panic among the people.
yeah, that's a challenge, particularly when the systems are unreliable. So there's the potential for a panic, and then people, everyone's trying to evacuate at the same time to a place, and there's a rush, and people could be hurt in that as well. So that should be considered in the design of the early warning system, making sure there's an action that can be taken that doesn't accidentally increase the risk. That's the last thing we want to do, is in trying to protect people, we're actually increasing the risk by putting them in some different type of harmful situation, like a traffic jam or something like that. And then the other challenge with these early warning systems is alarm fatigue. If you have many cases like this, where you sound a high alert and you say, this is a very high probability of a debris flow, everybody evacuates, and nothing happens, and nothing happens, and nothing happens, people will stop evacuating, and your system isn't very effective anymore. And so these are real, I don't have answers to those things, but it does make me wary about the use of these type of systems. Right now we're operating, we have a very large construction project happening in Squamish to manage debris flow risk, and I'll be talking about that in my other case study. But for that site, we have both of these types of early warning systems right now, and there have been many false alarms where we're telling people to evacuate when nothing happens. And we can do that because it's a construction site. It's not a community and people living there. So we have some control over that, but we're already getting questions. Even though we've had a debris flow. We had a debris flow 2 months ago, and the systems worked and everyone evacuated. Even though this event just happened, they already have alarm fatigue and they want to stop evacuating, even though their work site was buried in debris 2 months ago. So it's hard. Shows how quickly alarm fatigue can develop.
Landslide early warning system? If yes, I'm curious to know how effective it is working or something like that.
How effective?
Yeah.
Landslide.
Have you ever BGC install a landslide early warning system?
Yeah, so I guess I have the most experience with debris flow in steep creek sites. There are other people within the company that do have early warning systems set up for kind of slow moving landslides, but I can't speak to that, but we could ask a bit more. For debris flows, I shared the example of the Chikai site where we currently have an early warning system. And this is the first site in Canada that I'm aware of where we have a radar system. So we have this trigger upon hazard initiation type of system. And when we had the event in September, that system worked perfectly. The radar worked perfectly. We also had a trigger line, which is a weight and trigger the alarm, and that did not work. But the radar worked well, and Alex has things to add. Yeah.
No, can you describe what you mean by radar?
Oh, yes.
You-
Okay, thank you. So the in this
You have
in
a
this.
slide, I think, sure. Otherwise.
Oh, I do. This. Yes. Okay. So this is an example of a trigger upon hazard early warning system, and this is a radar system that can be suspended on a bridge or over on a cable over the channel, and the radar is shooting down at the water level, and you can set it so that when the water level or the debris level changes beyond a certain threshold, it sends a warning alert or an evacuation alarm to community members, to a construction site, to a road, and triggers different actions. Yeah?
Of the early warning system here in Nepal. For example, 2 or 3 months back, we had a very huge rainfall,
Yeah.
and the government was able to communicate with the people about how risky it was.
Yeah.
But like as Kesab sir said yesterday, the government was communicating in a way in which the public didn't understand it. For
Right.
example, they were saying there will be 300 millimeter rainfall.
Yeah.
For technical people like us, we might understand it, right? But for people, laymen, they might not understand it. So like if like government can say, okay, so 20 meters will be inundated, or for example, Kupandol, Pulchok, these areas will be inundated by rainfall. So if government can give in such way, that would be helpful. And that is not being done in Nepal. So my question is that being done in the case of Cougar Creek, or is it just like awareing people that a hazard is there, or does it also explain the extent of
Yeah.
the disaster in the case of Cougar Creek? So what has BGC done in that case?
That's so in the case of Cougar Creek, on that site in particular, there isn't an early warning system installed, but I agree that risk communication, need to do for the success of anything we're talking about in this workshop. And we run into this over and over again, where maybe we have as you said, the government. Sorry, I'm losing my mic again. The government had a good sense. They knew that this flood was coming. There were going to be issues, but finding the right way to communicate that, we go like this communication piece is very hard, and I think we're all still learning how to do it better. And I think that's where making sure for us as technical people and engineers and scientists to interface with other people who have experience in that. So it's not just us writing something that makes sense to our group. We should take what we write and ask our mothers if it makes sense. We should ask our children. We need to make sure that it works for all the segments of society that need to interpret our messages. And I would say that in Canada, sometimes we get that right. Same as Nepal, I'm sure. Sometimes we get it right, many times we get it wrong, and we're still learning about how to do it better. Because we have had similar issues. The atmospheric river event, the big rainstorm event that we had in Canada a couple years ago, there was many warnings about this. And when Highway 1 closed, so the highway that Lauren talked about, there's another road that goes around. But that road goes through even more mountainous terrain. It's more dangerous. And actually the only fatalities that happened in that event happened on that road. So when the main big road was closed, they chose to take the small road all the way around, and they were killed in a debris flow because we didn't do a good job of totally communicating. They didn't have the information to be able to say, we said, okay, there's 200 millimeters of rain, but they couldn't turn that into, that means don't use this road. Ask your mom if she understands. That's my advice. Any other questions? Okay. I think we planned 11:30 for break. Does that, something like that? Okay, I think I'll go a little bit more, and then we can have a break in a little bit. If everyone's still with me? Okay. All right. So we've talked about, let's see, do I have a, yes. We have talked about this initial prioritization. We knew Cougar Creek was a priority and that we needed to put in place short-term mitigation for Cougar Creek immediately. But then we had many other sites in the region that had also had events, that also had community infrastructure exposed to future hazards, and we needed to understand what to do next, what to study for these sites, and then what, if any, risk reduction was required to reduce the risk. And so I'm going to talk a little bit how we worked through that regional prioritization. So prioritization following this event was completed at a regional and local scale. And in Canada, we have provinces, and so the regional scale was done across the province of Alberta, so that's this whole area. And then we also did local prioritization using quantitative risk assessment just within this zone. I can't remember if this is on my next slide, so we'll go back to it. There. So the regional prioritization that was done, to give you a sense of scale, covered an area of about 200,000 square kilometers. So that's larger than Nepal. The province of Alberta is larger than Nepal. But Alberta has much less mountains, so we didn't have to deal with the mountain hazards across that entire 200,000 square kilometers. We had about 3,000 kilometers of highway and about 2,500 identified hazard sites. And one of the challenges when we were doing this regional prioritization is that we were needed to account for different hazard types, and then different hazard types and process types, and then those different process types had different consequence types. So that's what this slide lays out. So it shows, for example, you could have a debris flow, a rock fall, or a landslide onto a highway, and that was putting debris on the road, but the road surface was undamaged. So it's possible to come in pretty quickly and clean that. It closes the road, but it maybe only closes the road for a day or two. The next type of hazard consequence pair that we had was debris flows or debris floods coming across the road, and they actually damaged the road to the extent that a bridge or a culvert needed to be rebuilt. And this is something that's maybe going to take a week or a month to repair. Then we had a hazard type that was encroachment or bank erosion. So you have a road and you have a river coming in, and it's actually eroding the road grade. And that requires quite a lot of reconstruction, and that's also going to take several months to do. Or there could be flooding. And so this regional prioritization looked at all these different hazard and consequence types and tried to compare them. And hazard identification was done by taking, so we knew where the highway network was. We were also very fortunate in this case to know where the stream network was and to know where the alluvial fans were. So those were already mapped. And so this was a GIS exercise of intersecting those things. So we have information from all these gauge stations, from the stream network, and we can pile them all together. And when you pile them together, that's an intersection of the hazard and exposure, and we know what's at risk. This one's a bit dense, so I don't know how helpful this is, but really how this was done was we used the priority scoring approach that Alex introduced yesterday, and we came up with a risk index. So something that relatively took the information on what's the relative frequency of the hazard at each of those hazard sites, what kind of factors are affecting how bad the particular site is. So how far is the road from the river? How far is the road from the apex of a fan, the top of the fan that's coming in? What's the geology? What's the process type or the channel morphology? We looked at the average daily traffic, and then there was a vulnerability term about existing mitigation. And all of these things together could be used to bring in the different hazard types, the different consequence types, and compare them all in a single scale for prioritization. And then the products of that regional study is we had an online map that showed the different hazard sites and hazard types with the colors showing what were the priorities. It also included some information for each of those hazard types. What are the different risk management options? And then what, for each of those risk management options, what's an estimated cost? All right. Oh, okay. And then looking at the local level, so once this regional prioritization was done, we had some sense of locally what were the priority fans, but we still needed to know for those sites how much money was worth spending, how much risk was there, and how much money was worth spending. We knew we were going to spend a lot of money on Cougar Creek because it was a big problem. For these other sites, are they kind of okay, or do they warrant more effort? And in these sites, we decided to complete a quantitative risk assessment. And I don't know that I need this. I'm going to skip this bit. I'll go for it. Okay, so quantitative risk assessment. There's a few reasons to go through the detail of a quantitative risk assessment. One thing that I found in my career is sometimes you get clients that say, okay, go, like they tell you, I want a quantitative risk assessment done. And generally, as a practitioner, I am hesitant to do a quantitative risk assessment unless I really understand why to do it and that there's a very clear need. What is the purpose of doing this and what are we going to get out of it that's going to help me make good decisions? Because a quantitative risk assessment, so giving numbers to all those terms and all these different scenarios, is a lot of work. It takes a lot of time and it's not always necessary to do. So the reasons why you would choose to do it are to compare with risk tolerance thresholds. Some countries in the world have adopted risk tolerance thresholds that give a clear sense for that country or for that area or for that municipality what amount of life loss risk or economic damage from geohazards they're willing to tolerate. You'll notice from this graph that there is no consistency on what those tolerance thresholds are. There's many different lines. And so this graph shows number of fatalities and then the probability of fatalities. And there's different lines showing this would, sites that plot above would be unacceptable, sites that plot below would be acceptable. And this is a tool that exists in some places. So if you are working in a place where there are risk tolerance thresholds, that's a reason to complete a quantitative risk assessment because you need to be able to demonstrate whether you're meeting those objectives. Another reason to complete a quantitative risk assessment is to compare the geohazard risk and cost to other types of risk and cost so that you can understand, okay, the risk from geohazards is $100 a year, but it would cost me I could use that $100 a year to build a new health center or a new school. And then you can decide whether, or the government can decide, whether to spend that money here or to spend that money here. Another reason to do a quantitative risk assessment is to compare which measure is more cost effective. So in Lauren's example yesterday, to be able to say, okay, to build structural mitigation will cost this much, an early warning system will cost this much, and then I can understand and I can have all those dollar values behind everything. Because realistically, when we're justifying decisions for government or for policymakers, it all needs to be in terms of dollar values. That's really what everyone wants to know, if it's cost effective, if it makes sense to do. Oh goodness. I'm wondering if we should have a break, and then we'll go into risk equations. How's everyone feeling? Who would like a break now, or do you want to like deep dive into risk equations and then have a break? Put your hand up if you would like a break now. Put your hand up if you feel like risk equations. I'm getting a full mix. Okay. Biggle's not helping me. He's on the phone. Okay. Sorry to the table at the back. You guys were the ones who were feeling break. Wait, can we try again and have like everybody vote? Like this is your decision. So if you want to go on break now, put your hand up. Except everybody has to vote. Okay, if you don't want to go on break now, when I'm going to give, it seems equal, so I'm going to give the break people, just so I don't lose everybody. So you can have is this okay? 10, 15? When you walked out of the room 15 minutes ago, because I keep circling on the order to go through them, so we might go through them in back and forth a few different times. But what we're going to do in this next, I think we have 45 minutes or so until 12:30 when we have another guest lecturer coming to speak. So in this period, I'm going to explain a bit about how to work through a quantitative risk assessment, and then we will do a group exercise at your tables where we walk through that as a team. So we talked about prior to the break why we do quantitative risk assessments and some of the reasons, and I shared that I am generally hesitant to jump to doing them, but there are cases where they are very useful tools. So let's say that we're working on a project where it has been decided that a quantitative risk assessment is the best decision tool to help us decide about risk assessment. And so in order to quantify the risk, we need to quantify a few different things. We need to understand the hazard, same things you're used to now, hazard, exposure, and vulnerability. And there's a few sub-questions. We need to know how big is the hazard, how often does it occur, what areas does it affect. Then we need to know where are the people or the buildings, the elements at risk, and how long are they there for? And then we need to know how likely are deaths or damages given impact. And there is no single answer to these questions. And that's why when we approach a risk assessment at BGC, we use different risk scenarios. And this ties to what Alex introduced yesterday and what I introduced earlier, which is that a hazard isn't just a process type. A hazard also has a size and intensity and a likelihood. And so we look at different hazard scenarios. We calculate risk for each of those hazard scenarios. And then to get overall risk, we sum them together to get the risk of all the hazard scenarios together. And so what that allows you to do is it allows you to answer a bunch of different questions that can be useful for your mitigation design process. You can say, okay, what is the risk from a 10-year event, or what is the risk from a 100-year event? It lets you understand what is the risk to this building, or the risk for a person in this school. What is the risk for all the people in the school? What is the risk for all the people on the fan, or all the people within the landslide runout area? You can answer a lot of different questions. So quantitative risk assessment can be a really useful tool. So we understand that we're gonna calculate risk, and we're going to do it for different scenarios, and those hazard scenarios have characteristics related to size and likelihood. So this is the risk assessment, or the quantitative risk equation that we use. Total risk is calculated by summing the risk for each scenario. So we do this for as many different scenarios as we have. And it's made up of a couple different terms. We have the annual probability the hazard occurs. So first, there's the hazard scenario is defined. We're calculating risk for, let's say, a 100-year, let's make it a rockfall, because otherwise I keep going to debris flows all the time. 100-year rockfall. So we know that 100-year rockfall has a certain size. We're going to calculate the annual probability, that's the 100 years. We can figure out the spatial impact probability using different runout modeling tools. Where is that event? Given that this event has a certain size, where is it going to go? We can figure out what's exposed that's there, whether it's people, whether it's dollar value of buildings. What's the temporal probability? What's the likelihood that the thing is there? If it's a building, it's not going to walk away, so it's always there. If it's a person, the child might only be in school for 6 hours a day. A person might only be in their office or in their business for 8 hours a day. Someone is maybe staying at their house for more hours of the day, so we would account for that to calculate the risk. And then we would have a term for vulnerability. So given impact by the hazard, what is the probability of loss? All right, so I think my slides got mucked up. Okay, so scenarios using different, so Alex presented this idea yesterday that for any different hazard type, we have a frequency and magnitude relationship. If you remember the graph that Alex had yesterday, it was for earthquakes, and it showed that for earthquakes and for many of these hazards, there are more small events and fewer large events. And we can use the scientific tools at our disposal, and we can talk a bit more about that later, to understand what is the frequency and the magnitude of the different hazards. And then once we have that relationship, we break that relationship into smaller chunks into these scenarios. So actually, hazards occur on a continuous distribution. You can have a debris flow that is 10,000 cubic meters, 11,000 cubic meters, 11,001 cubic meters, 22.5, like you can have all these numbers, but we're not going to do hazard scenarios for every single different debris flow that could occur. We're going to put them into bins. So we're going to say, what is the risk from a debris flow that is 10 to 20,000 cubic meters, 20 to 30,000 cubic meters. So that lets us simplify the number of times we need to do the risk calculation a little bit, rather than doing it for absolutely everyone. And so just as an example, you might have a return period and then some typical magnitude that you've figured out by doing a hazard characterization or hazard assessment study. And this is called the frequency magnitude relationship. So, actually, would it be helpful? No, I don't have enough time for that. I promise I will tell you about hazard assessments later, because I recognize that that's a gap that we haven't filled yet, and so I can share a little bit about that later. But I want to make sure that we have enough time for this group exercise to walk through the quantitative risk assessments. So, let's do an example of how to calculate risk for a single scenario, and then we'll branch out from there. So what is the chance of a fatality at a hazard site due to a landslide of a certain size? So we're going to start with H. Let's say that the hazard probability for that size is 1 in 10. It's a 10-year event, so that's 0.1. Well, keep doing that. Go away. I don't know how to make it go away. There we go. Okay. Look. And then we can do a runout model. We can figure out what the spatial impact probability for a certain spot is. And in this case, we're going to say that there's a 50% chance of this landslide hitting this house. And then we're going to say the house is certainly there. It's not going anywhere. It's there all the time. I realize I didn't adjust this, but that's all right. And then the vulnerability is the probability of death given impact by this event, and it's 50%. So here we would say the risk for this scenario is there's a 2.5%. So you take all those numbers and multiply them. There's a 2.5% annual probability of a fatality. All right. So that's an example for a single scenario. At this point, I'd like to start doing the group exercise. And what we're going to walk through as a group, so I'm going to put up a question on the board. Don't worry, I'm not going to set you loose to jump right to this point. We're going to break it down into steps. But what we're going to be working towards is developing a scenario-based event tree. So we're going to use this idea of scenarios, and we're going to build an event tree to describe debris flow risk for a community, and then we're going to do a simple quantitative risk assessment calculation to figure out risk for the school within this community. All right. And to do this, we're going to use the whiteboard. Okay. Oh, it came to the whiteboard already. Great. All right. So, let's say we've got our, don't want the eraser. There we go. We've got our watershed, and we've got our fan. And this is a debris flow watershed again. And on this fan, we have a number of houses, and I'm going to circle this one because this is our school. Oh, right, there's a pen. I had one here. Here we go. Perfect. Thank you. Okay. This is our school. And we have done a hazard assessment study already, and we know a frequency magnitude relationship for debris flows in this site. So we know that, oh dear. Nope. Okay, now I'm like scared to touch it because it zoomed on me. And I don't know how to not zoom it if it. It won't draw? Oh wow, it goes big. Wow, cool, oh good. Okay. Are you guys just like all used to this? Do you have these everywhere in your lives? We've never seen one before, so it's really cool. That's why we're like total noobs though. Okay. Now I want to like, no, that's not what I do either. All right, so we have our watershed, we have our school on our fan. And we've got, okay, so let's call this return period. Is everyone familiar with the concept of return period? Nope. Oh, Alex was shaking his head for you, and you guys were all like, yeah, we got this. Good to know. Okay, so we're going to say that the 10-year return period, and we have a, oh, do I do small, big? Okay.
Small, big.
Yeah, I'm just trying to think about how best to teach it. Anyway, okay. I feel like I've gone down a road. Okay, so we know that the 10-year return period has a certain volume. Let's say that's 10,000 cubic meters. Let's make it big because it's, and then 50,000 meters cubed. And then we can do a runout model to figure out where these different events go. And let's say that they both hit the school. Okay. How do I like slide it? If I want to move that back up over there. Ah. Sorry. That's okay. I can make this work. You do it. What if I do it? Oh, put it down there. Then we can draw over here. Okay. Okay. I think I'll keep that there for now, and then I can like zoom in and out on it. All right. So we've talked about this idea of different risk scenarios. A useful way to visualize risk scenarios and make sense of them all in your mind is something called an event tree. An event tree starts with a hazard. So in this case, let's say, look at this. There is debris flow hazard. And then, so this hazard exists, and then there's different scenarios that could happen. I'm gonna start by mapping out one of the branches of the event tree, and then the question to you and your groups is gonna be to build out more of the event tree. So I'm gonna show you what one branch looks like, and then you're gonna try building out some of the other ones. So we have a site with a community with a debris flow hazard. The debris flow could either, in a given year, the debris flow could not occur. Nothing happens. Or there could be a small one, or there could be a big one. Now if we take this small branch, this small event could either, so we're going to work through this event tree for the school. So this is debris flow risk for school. So the small event has occurred, and it could either reach the school or it could not reach the school. What is the risk if the debris flow, a small debris flow occurs and it does not reach the school? What's the risk of that scenario? Yeah. All right. And then the debris flow occurs, it's small, it reaches the school, and we're trying to calculate life loss risk. So what's the next thing we care about? So let's put this up here. Risk equals hazard times spatial times temporal. Yeah. So the next term here is temporal. So yeah. That one is
As the number of children.
yeah, we can do group risk. Okay, yeah. Put that one in. Okay, so it reaches the school. What's the question that we're asking for temporal? So we're yeah, are there people there? So yeah, school is open, school closed. And then if the school is open, let's say let's just do one branch, I think. Make it easy. There's 100 kids. And then we're going to say if the debris flow is small, reaches the school is open, and there's 100 kids, what is the chance, what's the vulnerability, what is the chance of a fatality if that small debris flow reaches the school? And let's say, and that's where you would have a fragility curve or something to tell you information about what could happen for people in the building that was built in that certain way at a certain hazard intensity. And so let's say if the small one reaches the school, like I said, on to the percent, it's just at this point, so then there's 100 kids, so then there could either be, like, oh dear. Oh wait, I can do this. I'm trying to zoom out. I'll get there. No. No. No luck? Oh, am I all the way out? Maybe I'm all the way zoomed out. Okay, anyway, so if there's 100 kids, then you could either have a path where there can be how many fatalities? So let's just say X fatalities. I guess that's the risk, yeah. Okay, so we worked through that branch for a small debris flow hazard. I'd like you to draw out the rest of this event tree and add the path for a big debris flow hazard. Cool. Sure, okay. Sounds good. Can I ask? Yeah. Can you turn my mic off? Excuse me.
Yeah, let's see what you have. Show me what you have. Yeah, let's get started.
Each time you make a branch, you're moving to the next one. So you want each, yeah, so then it's yeah, 2 per time.
Hi everyone. We're going to come back together for a couple minutes. If your table feels like you kind of understood where things were going, put your hand up. Of the event tree for big events. I'm not volunteering you to say anything. You just have to. If you don't want to, you don't have to. But I think you can do it. We can be a team. Come help me. I'm very bad with this board. I like how you left lots of space in your event tree. That's going to be helpful. I should have told everybody to do that. So, on their event tree, they have the event is big. It either, oh dear, reaches the school or doesn't reach. Not reach. All right, what did you have? Maybe another group. What comes after the big event does not reach the school? Did you draw anything else after that? No, nothing happened. It's all done. What comes after the big event reaches the school?
Either the school open or not.
Perfect. So that's our temporal piece. So school open or not open. All right. What comes after the big event reaches the school and the school is closed?
Infrastructure damage.
No, what happens if the school is closed? So I can't hear. Yeah, okay. Good point. So the building damage, you guys, good job. I was just focused. We'll just stick to life loss risk. But if you were doing a full event tree in which you were looking at different types of consequences, you would probably carry all of those through. You're right. So then after school is open, what comes next? What's then now we're on to the exposure term.
Kids and life and infrastructure losses. What student can be happen?
So, how many students? Yeah, 100 kids.
X1.
Can't read that one. Oh, infrastructure. Yeah, okay, cool. Yeah, we're gonna stick with the kids. And then I realized that this one I could describe better. So for vulnerability, there's different cases, and maybe there's a case where there's no fatalities, some fatalities, or all. And then same thing, no, some, all. Okay, the next piece we're going to do, so now we have this is an event tree that helps us understand the different risk scenarios that could occur. Each of these branches on this tree, every time it splits, that makes a different scenario. I'm a little scared to draw in my tree in case I totally mess it up, but I'm going to take the risk. So this pathway is one scenario, and then each of these other pathways is a different scenario. So now what we need to do a quantitative risk assessment is to calculate the risk for each of those pathways. To do that, there's a few rules that we need to follow. One of the rules is that at every branch of the tree, you're going to assign a probability at each branch. And so there's a probability in each year that the debris flow hazard doesn't occur. There's a probability that a small one occurs, a probability that a big one occurs. Those probabilities within this piece, and this piece, and this piece, always need to sum to 1, so that you are counting for the full range, 100% of probabilities. Otherwise, you're missing something. If you only carry through certain scenarios, then you're missing some component of the risk. So, and then when you assign those probabilities, you can work through and estimate risk for each branch. So I'm going to start out by labeling some probabilities on my event tree up here. I apologize because it's become a bit of a spaghetti, bit of a mess. So it might be tricky, so ask me if there's some that are confusing. And then the ask to you is going to be to put those same probabilities on yours, and then make a list of each of these scenarios that you have, each of these branches, and just multiply through the risk and figure out the risk for each scenario. So we have our debris flow hazard. For this event, I'm going to say that there is a 90% probability of nothing occurring. So we're going to put 0.9 on this branch. We're going to say there is a 9% probability of a small event occurring. 0.09. And then what goes down here on the big branch? Thank you. Okay. Now, we're going to look at the scenario for a small debris flow, either reaching the school or not reaching the school. You can kind of, because this is a hypothetical example, we can just pick a number here. So I'm going to say that there is it's a pretty small one, so maybe there's a 20% chance, 0.2, of it reaching the school. What is the chance that it does not reach the school? Perfect. 0.8. Now we're moving down to the big one. Probably, anyone just want to pick a number for what's the chance that the big event reaches the school? 0.7. All right. This is a big one. Okay, what's the chance of it not reaching the school? Perfect. You're getting the hang of it. Okay. And now temporal probability. This is something that we as engineers, when we're estimating this, often we're working with community members. If it's a communities project, or we're working with the person managing the road or something, to understand the temporal probability. So in this case, if I was doing a study for the school, I would ask my clients, maybe it's the municipal government, what are the hours that your school is open? How much of the day is your school open? So how long is a school open? How long is an elementary school day in Nepal? 6 hours, and then how many days of the week? 6 days a week. Okay, so we have, it's open for, so there's a 0.25 times 6/7. I'm not going to try to do that, but you're welcome to. You can pull out a calculator. And then the chance that the school is closed is 1 minus that. There we go. And same thing for these ones.
I couldn't hear in the back where that 0.25 times 6/7 comes from.
Okay, so I heard from the group that schools in Nepal are open for 6 hours a day. So that would be, let's do 6. Oh goodness. I'm gonna change the 0.25 to 6 out of 24, because that makes more sense to everybody. There we go. So, goodness. So this is 6 out of 24, so that's 6 out. Schools are open 6 hours a day out of 24 possible hours, and then they're open 6 days a week out of 7 days. So it's 6/24.
6 over 6.
And times. Yep. Thank you. Oh goodness. I really want somebody else to come take a turn drawing on this board, so you can enjoy. Okay, there we go. So that is our temporal probability that the school is open. There's people in the school. And then we have, if the school is open, we know there are 100 children there. And then we would have a function that, I'm actually going to erase this stuff. We would have, so I've been calling them fragility curves. Someone in the audience pointed out that a type of fragility curve is a depth damage curve. And so you can have depth damage curves that correlate a certain flow depth to damage in the building and infrastructure. You can have the same kind of thing that says for a certain depth or velocity or flow intensity, what is the likelihood of fatality in the building? And so we're going to say that for this small debris flow, if it reaches the school, then for each person, it's probably pretty small. So let's just say that it's like a 1%. Let's make it more interesting. We'll make it 5. There we go. 5% chance of fatality. And then for the big event, let's say that it's a, oh, that's way easier. Okay. Never mind, cursed myself. Okay, let's say that it's a 30% chance of fatality. And so what I would like you to do is work through for the event tree that you drew out and calculate for each scenario that we've done. So for each of these branches, the answer that this math will give you is, for that scenario, how many fatalities are expected. Any questions before you start that?